So waiting time quantum metrology. Let us assume that we have some kind of physical system, and the system only spits out signals at discrete times. We can have different signals. An example can be, we can keep this in mind for the entire presentation, for example, the usual 3-level maser model. Okay, so we have 4 different kinds of emissions of quantum jumps, and they are all localized in time. So what we can expect for a trajectory on one of the observables here is a plot like this. An experimenter who wants to measure, to do something on this system could record something that we will call a measurement record, which is made of channel of specific type of the emission and time at which the emission is recorded. So this is all what's available for an experimenter. Now the problem is how, let's say that we want to use this object to measure something which is encoding, a parameter which is encoded somewhere in our physical system. For example, in the case of a 3-level maser, we can think of the temperature of one of the 2 bags. And then the question is, how precisely can we estimate this parameter by starting from an object like this? So the presentation is structured like this. I will start by introducing quickly the main ideas of estimation theory, then go over the formalism of quantum jump parameters, just to set the stage for the discussion. Then I will need to restrict a bit to a subclass of processes for which something can much more easily said analytically. We will then generalize to the entire class of possible quantum objects, and finally look a bit at the information compression problem. So the idea of estimation theory is very simple. We assume to have a probability distribution which has a functional dependence on some kind of parameter which is encoded in the probability distribution. We then sample the probability distribution, so we generate a string of random variables which are sampled from there, and we try to estimate the value of the parameter by starting from the sampling. So we will define an estimator, which is basically a machine that given the sample, spits out the candidate value of the parameter, which hopefully will be close enough to the true value. So in particular, we can talk about, at this point, the precision of this estimator, and assuming an unbiased estimator, what we get is that the precision is bounded by the Kramer-Rao bound. So by the inverse of this quantity, which is known as the Fisher information. So this means that the expectation value, so the mean square error between the estimator and the true value of the parameter is bounded from below by this quantity. The Fisher information is defined like this, so it's basically minus the expectation value of the second derivative of the log of the probability distribution, derivative with respect to the parameter, and somehow represents how strongly the probability distribution depends on the parameter. So we can think that if the probability distribution depends very heavily, very strongly on the parameter, the estimation task is easier than if the probability distribution exhibits a very mild dependence. Let us now set the stage of our description using the formalism of quantum jump unraveling. So we will assume that the dynamic of our physical system is governed by this GKSL master equation, and in particular we can see each of these LK operators as a jump operator. So we can think of our process in terms of a sequence of jumps and no jump coherent evolutions. So we'll define the jump superoperator like this. This is what happens to the state when it jumps, except for normalization. This is what happens to the state when it does not. It's connected to what happens to the state when it does not jump. Here it's useful to define what is this M. We will assume that we, in general, are not able to monitor all the jumps. So in some cases, for example, an experimenter is not able to have a detector which is sensible to all the possible jumps that can happen. So we will define a subset of jumps, of emissions that can be actually recorded, which will be this M. Now, if we think of a process like this, we can represent it in 2 different ways. We can think of it in terms of what we define as the measurement record, and we can call this the N ensemble. In this representation, the measurement record is represented as emission channel, as a sequence of pairs, emission channel, emission time. Another possible representation is to subdivide the time in infinitesimal time intervals dt, and in each of them, we can say, does the system jump or does it not? And if it doesn't, we will just record a 0. If it does, we will just record the label for the specific jump channel. The two representations are equivalent in the long time, in the long time or long n limit. Okay, so let us now start from an object like this and ask, okay, what's the maximum precision that we can achieve for estimation tasks by starting from an input like this? Now, in order to compute the Fisher information, one has to start with the probability, of which then we need to take the derivative. The probability looks something like this. So we start from an initial state. Usually, taking the steady state is the easiest strategy for formal reasons. And then we have a jump. Then there is a given time of no jump evolution, or at least no monitored jump evolution. Then we have another jump, and so on. So what is the Fisher information contained in this measurement record? Now, this is clearly not an object on which we would like to compute an expectation value. It's simply not feasible. But we can say something in a sub-case, which is the one of renewal processes. So a renewal process is something like a process for which, after each jump, the quantum memory is completely lost. For example, in the standard representation, in the standard model of the three-level maser, what we have is that after each jump, we know exactly in which energy idle state the system is, which means that the quantum memory is completely destroyed after each jump. In other terms, we can say that the jump superoperator acts for each jump as a point map on the initial state. Now, if this condition holds, then we can much simplify our probability. So we can simplify a lot this expression, this equation, and you can write it in terms of a product of objects like this. Now, each of these objects is what is called the waiting time distribution. And the idea is that it is the conditional probability distribution that if I have an initial jump in channel K, or Q, okay, let's use this, then what is the conditional probability of having a jump in channel K after a time tau sees the first jump? Now, something which is interesting to see from here is that this takes the form of a Markov order 1 process, so a Markov process, in terms of the pairs, jump channel, jump time. If furthermore, there is only one jump channel, at this point, this condition on the previous jump channel is trivial, and we get directly an IID process in terms of the jump channels. Okay, for renewal processes, by exploiting this representation, we can at this point write a simple and analytical expression for the Fisher information, which is what we find here. So in practice, the Fisher information depends on an object which is only dependent on the waiting time distribution. And in practice, it's the Fisher information of the waiting time distribution. We see here the n scaling of the Fisher information. So the Fisher information grows linearly with the number of jumps. This is a result which is completely expected for processes for which there is for which the correlation die quite quickly. In this example, okay, we have again the three-level maser, and here we represent some of the waiting time distributions, in particular all the ones that have as an initial jump the yellow one here, so from 2 to 1, with an emission in the right path. And here we represent the corresponding Fisher information. Okay, let us now try to go beyond this renewal case. Going beyond the renewal case is complicated because at this point we actually have to deal with this probability distribution, and it's not a very tractable object. Just to keep in mind something, let us consider this 2 qubits model. So we have 2 qubits, each one of them has its own Rabi frequency. They are coupled in this way. and one of them can jump with an operator which is this. Now, I represented here what happens to the number, to the expectation value of the number operator on a trajectory, and I think it expresses quite well what no renewal means. Now, at each jump, a jump is something like this, so an abrupt change in the index is represented by an abrupt change in the expectation value. When there is a jump in channel B, when there is a jump, qubit B gets completely reset, but qubit A doesn't. So some kind of quantum memory is carried also during the jump. This is a good and simple example of a renewal process. So how to compute efficient information? So how to define the precision in this case of non-renewal processes? What one would have to do in principle is to compute this integral here. One would have to integrate over all the possible jump times for all the jumps, and then sum over all the possible jump channels for all the jumps. This is clearly not something feasible. It's a space over which to integrate which grows exponentially. So it's not possible to do it like this. Therefore, another method was found more or less a decade ago at this point, and it involves the use of what we will call a monitoring operator. Let us first define an unnormalized conditional state. So on a specific measurement record, we start from the steady state, and then we repeatedly apply the coherent evolution, the no-jump evolution, and the jumps at the specified times. And let us define this object here, psi. Now, this weird object, like a derivative of this conditional non-normalized state, has this very nice property. So if we take the trace and square it, and then take the expectation value with respect to all the trajectories, what we find is exactly the Fisher information. The reason why this object is so nice is that at this point we can calculate the Fisher information over trajectories. So instead of computing this integral by using a grid-like method, we can compute it actually by using a trajectory method, which naturally allows to weight much more the relevant contributions and to avoid spending a lot of time integrating non-interesting regions. Now, in particular, the way so we have to evolve this object on quantum trajectories. We will evolve the state, and at the same time we will keep evolving also this operator. We can write evolution operators for this object, and we will evolve them in parallel, and in the end compute the Fisher information like this. Now, the way in which sometimes we integrate this kind of dynamics is to simply discretize the time, so we assume a time step dt, and at each time step we ask, does the system jump or does it not? And then we apply the corresponding Krauss operator and we move on. The problem with this approach, especially if we need a large number of trajectories, which is usually the case when we want to do Fisher information computations, is that in most cases of physical interest, the time scales of the Hamiltonian are much quicker than the time case of the jump dynamics. Which means that, as we can see here, most of the time, like the vast majority of the time steps, will not see any jump. So we'll spend a lot of time computing parts which are not interesting for our purposes, if we are only interested in the jump dynamics. Therefore, we introduce this algorithm, this new algorithm, which is called the Gillespie Fisher algorithm. Gillespie comes from a well-known algorithm in classical statistical mechanics. The idea is that we generate the waiting time distribution, we sample from it, we evolve according to the waiting time distribution, and then only in the second time we specify in which channel the jump will happen. Now, the significant advantage of this algorithm is that it allows for a large amount of relevant and numerically heavy quantities to be pre-computed. So we can pre-compute them, store them, and each trajectory will employ the same quantities. So we don't need to recompute them all the times. This actually gives a nice computational advantage in many cases of interest for our project. What we see here, so if we do this, This is an application to the 2 qubits model that I presented earlier. So we have time and the Fisher information as a function of time. And what we see averaging over many trajectories is something like this. It's clearly noisy because it's all computed over trajectories, but what we see is a linear behavior for a long time, in the long time. Now, even though this is not a finite Markov order process, so this is not a very precise argument, the linear behavior of the Fisher information is usually correlated with a decay of correlations. So if correlations decay fast enough, we expect to have a linear behavior of the Fisher information. Here I highlighted in black also one of the individual trajectories of this trace of psi squared, which shows, as you can see, very abrupt jumps in correspondence with the jumps on the individual trajectories, and some small oscillations whose frequency is related to the Rabi frequency of the electrons. Now, okay, when we see a plot like this, we can ask, can we say something analytical with respect to the jump rate? Is it possible to say something? Actually, yes. So, in this case, we need to represent our process, though, in the n ensemble. So, we have to think of it in terms of, we divide the time in dt long infinitesimal time steps, and for each time step, we record 0 when no jump happens, and a label for the jump when the jump happens. So we get a string like 0, 1, 1, 0, 1, 0, 0, 0, 2, or something like that. Now we can use this, this equation, which expresses the Fisher information, the joint Fisher information up to time t plus 1, in terms of a slightly shorter joint Fisher information up to time t, plus an update term, which in the dt, which goes to 0 limit, takes the form of an infinitesimal increment of the Fisher information. Now, we can, at this point, write an equation for the Fisher information rate. And this equation takes the form of the expectation value of this quantity, which reminds a lot the form of the Fisher information. And it's written in terms of the stochastic current, which is this object here. Curiously enough, even though we have multiple different stochastic currents, if we have multiple channels, the Fisher information rate does not include cross terms. So they do not interact one with each other with respect to the information they carry about the parameter. Okay, finally, in many experimental situations of interest, we do not have access to the full measurement record. For example, getting back to the initial example of the 3-level maser, we get in many, if we get back to the example of the 3-level maser, usually it's not possible to record photons going from the bus to the system, but it's only possible to record photons going from the system to the bus. Therefore, this takes the form of what is called a compression or data processing on the measurement record. So we have to neglect some of the jumps. This situation is described in terms of the data processing inequality. So if we have some map applied to our sampling, we can only say that the Fisher information is reduced. This is, if you think about it, very reasonable, as soon as the map does not depend on the parameter. Obviously, we are not allowed to plug further information into the system by using the map. So, a common situation for this is what I presented earlier, so the idea of partial monitoring. Not all the channels can be recorded. Some of the channels are not accessible experimentally. This reduces in reduction of the set of monitor channels M, which we discussed earlier. Another possibility is the one which we call channel mixing. So for some reason, our setup is not able to distinguish two different jump channels and can only record the fact that some jump happened, but without being able to distinguish exactly in which channel our jump happened. This is a further post-processing or a further compression. What we see is something like this. So we have, this is for the 3-level system again. We have that the Fisher information, if we monitor all 4 emission channels here, is this. If we only monitor the outgoing jumps, that is this one and this one, so from 2 to 0 and from 2 to 1, what we get is the red one. And if we further assume that the two jumps cannot be distinguished, we get further reduction of the feature information. A final note on the nature of the processes. Now, partial monitoring does not transform a renewal process into a non-renewal process because it doesn't change the nature of the map. On the contrary, channel mixing does. So just because the sum of 2-point maps is not usually a point map. Therefore, when we deal with the three-level system, the three-level maze, which is usually a renewal process, it's completely possible that if we merge two different jump channels, we will get a non-renewal system, which is also the reason why we need here to use a stochastic simulation. We cannot use the equation we presented at the beginning. Thank you.
Left with time for questions, Gerard.
I better stand up so you can hear me. There's one example of a laser where you can keep track of the incoming photons as well, and that's the micromaser. I don't know if you've thought about that. So the micromaser is a beam of velocity collimated atoms prepared predominantly in the excited state that traverse a microwave cavity. And you can check to see if it dumped a photon by looking at the atoms after they leave the cavity, and you can look at emission from the cavity. So you could have both in that case.
Thank you.
Any other questions?
Maybe I can ask a cheeky question because I've discussed this stuff with you before. But so to speak, the situation where you're saying that you cannot distinguish between these channels, sort of you're trying to understand and to be able to predict the evolution of a system when you're only able to recover partial information. You can sort of see this in the Fisher information. And are you guys able to relate this to sort of this, like, how many hidden Markov states you need to recover something? So like this lack of being able to read out all the information. Can you show that, like, in situations where the underlying dynamics has little complexity, so like few hidden Markov states, you might actually not need to know all that information. Like, so I don't know if it's clear.
I mean, I would say that if I did not need the entire information, so if the compression could not change the Fisher information, I could see the two curves overlapping. While, I mean, this means that all the information is needed. If I just ignore something, I will worsen my estimation.
Okay, one last question.
So, a 6U considers parameter estimation using the waiting time distribution. And if we know all the information about the waiting time distribution, I think it is possible to reconstruct all the jumps. So I want to know the difference between the waiting time distribution, Fisher information for the waiting time distribution, and normal jump distribution. So why you are make particular emphasis on waiting time distribution?
Yeah, I mean, like the idea is that the waiting time distribution is a well-defined object when we have renewable dynamics. Like when actually we can factorize this probability, the probability for a trajectory in terms of this waiting time object. And in this case, it's nice to be able to write the Fisher information relatively like this. But in general, like in a no-renewal system, the waiting time distribution is not a very well-defined object, I would say, because at this point it becomes dependent on the initial state, since the first jump channel does not completely erase the quantum memory, I would say. Does it make sense?
Okay, let's discuss it.
Yeah.
Let's thank Michael again.